Here is already good morning. First of all, I want to thank you because you're being part of this today. And well, thank you both of you because today's topic is gonna be pretty interesting. And we are gonna be asking you so many questions or a couple of questions. So, well, I want to introduce Marloes, Peeters. That she's gonna be talking about something pretty interesting. It's about thermometers, and also our teacher, Professor Jonas Gruber. So I'm gonna be also talking and asking a couple of questions. So thank you very much. You Jonas, if you wanna say something, go ahead.
Yeah, thank you, Rebeca. Gracias. Eu vou falar em português porque Marloes entende português muito bem. Já esteve no Brasil tantas vezes. Então, temos hoje a honra de ter como convidada a professora Marloes Peeters, da Newcastle University, do Reino Unido, e que tem sido nossa colaboradora há mais de 10 anos, desde 2012, quando ainda estava na Universidade de Hasselt, depois foi para Leuven, e depois para a Universidade de Manchester, e agora está na Universidade de Newcastle. E essa colaboração muito frutífera envolveu o envio de mais de 10 alunos nossos para estágios em seus laboratórios, alunos da Escola Politécnica da USP, depois de Engenharia Química, alunos da Faculdade de Ciências Farmacêuticas, e é um grande prazer tê-la aqui e apresentando, então, uma palestra para pessoas, para o público em geral, né? Então, vai ser uma coisa que todos vão poder entender facilmente e um assunto realmente, eu estou muito curioso. Então, eu não vou me alongar mais. Essa palavra para a professora Marloes Peeters.
Okay, well, thanks so much for your introduction, Jonas. And so, yeah, it's afternoon here. So as you mentioned, I'm in the United Kingdom, quite far up north. So it is a little bit cold here today, but unfortunately we can't all have the weather like we've got in Brazil. So I'll talk a little bit about sensors today and what you might all know as a sensor. So you've got, for instance, your nose to smell things, your ears to hear things, your skin when it's like warm or cold. So within our body, we've got many different types of sensors, okay? And unfortunately, I think because of this pandemic, we also have been having to do lots of lateral flow tests or maybe PCR tests. So I think the general public knows a lot more about sensors nowadays than maybe before. But in our body, in most sensors, we use something that actually comes from within our bodies. So if you would have, like, and I know the talk before this was about COVID, if you would have like an infection or like a bacteria or something foreign that invades your body would have these antibodies that can recognize, for instance, if there's something foreign in your body, and then they'll signal to your immune system. And these are very good at very selectively identifying what's happening. And our body is by far the best at detecting those things because it's all natural. So what a lot of people actually do, like in sensors, is that we use these antibodies, is what you have in your body to, selectively detect things. So for instance, you've got your lateral flow test. I should have taken like an example here. You have this little stick and you might not be able to see it, but what's on there are like antibodies for COVID-19, and then you would see this color change when something is happening. So very easy, everyone will know how this works now. We've seen these colors on the lines. But what I'll talk today about is that actually what I'm interested in Newcastle University is making different tests. And these tests are based on a temperature change. So imagine something which is, I mentioned like thermometer, so it's not exactly the same as a thermometer in your house, but it's kind of like a smart thermometer that can still detect things. And the smart bit here is that actually this thermometer is modified a little bit with some plastic. So we would have something which is inspired on the structure of the natural antibodies you've got in your body, but then it's a plastic material. And I'll have to talk here a little bit about what plastics are, and I've thrown out some things a little bit, because when people think of plastics, they always think of plastic bags, and you might think of the clothes that you have and other things. But these plastics are made from polymers, and I thought it might be good at least to kind of show something here, which I'm not sure will work. But I've drawn some things in orange because I am Dutch, so at least we'll go for the other side. Give me a second so I can get. So I don't know. You might see it the other way around. No? Okay, I'm not sure.
Yeah, I can see it again.
Okay, good. So the way this works is I'll need to explain what a polymer is. Okay, so polymer comes from the Greek, so it says poly is many, and meros is parts. So it basically means it's many repeating parts. In your body, you've got DNA, so that's a natural polymer. Okay, so just to kind of give you a bit of an understanding, so these are really long structures, and you can see here a little bit like a little neckness. So all kind of the same units that kind of repeat each other. So when we talk about plastics, that's always a synthetic, so a man-made polymer with some additives in it. So these additives are to manufacture it better, because plastic also means moldable. So we have this polymer material which we can mold into a certain shape. And that's the kind of technology that we work with. Because I think when we work with plastics, people, as I said, automatically think of these plastic bags. But we can also mold these type of structures which are very similar to the antibodies that we've got in our body. And that's just to give you like an understanding of the polymer material that we work with now. We can work something, which we can give a polymer material some kind of memory. So like we have biological memory. So imagine when a child is born, the first things you see are their parents, and you kind of follow them around. So think of, for instance, you have like the hatching of like when you have ducks, or not necessarily ducks, when you'll kind of see them nicely following in a row. Or for instance, you've got an egg that was hatching. And I always give this kind of example of Jurassic Park in my lectures. You have a dinosaur which is hatching, and the first things it sees, it thinks they are their parents, and it will recognize them. So the way you have this biological imprinting, so how it kind of forms that kind of connection with what it sees and what it recognizes, molecules can actually do something a little bit similar. So you would have something, and I'll try and kind of draw this out a little bit. We have something that we want to detect. So let's say that's that kind of like little dot here. Now what we do is we have some materials that kind of assemble around it so they recognize it. And then we polymerize them. So you don't really need to understand what it is, but then we basically form like a network. So we basically have got some kind of material. Into which whatever you want to detect is kind of in there. Okay, so something we've got, and then we have something which is, because these polymer materials, as you know from your plastic, they're quite stable, so they lock it into place. And then we can do something smart where we can remove the material. So we can wash it away. So what you end up with, I used to call it like a little Swiss cheese. So you've got something here where you've got like cavities in here that are exactly the same as what you were kind of imprinting with in the beginning. So let's say if you've got something round, then you would get like a nice cavity which has this round shape. If you would have bacteria, which can kind of be like elongated, or can be square, or another type of shape, you would get a different shape in there. So you get these little, like essentially like little holes that match very well with the size and the shape that you would want to detect. But they also have a bit of like chemical binding as well, which you don't really need to understand so well. But just imagine that you've got on a very, very tiny scale. It's not possible to see it unless you work with bacteria, which are relatively big. Then you can put it under a really good microscope and you can actually see those holes. it has these really very specific binding sites for what you want to detect. Now, and this is what we call molecularly imprinted polymer. So it's a plastic material that has got these binding sites, and actually the affinity is just as good as what the natural antibodies have in your body. So we take this and we make something which is man-made, so it's synthetic, but it has the same kind of performance, so it can detect at exactly the same rate, but it has got a couple of advantages. So first of all, lower cost, because that's the first thing industry kind of wants to think about. You can manufacture it in very large quantities, so you can make big examples of it. It's very robust. As you know, these polymer structures, anything we've got in our body normally works under a specific temperature. So we are 37 degrees, so it prefers to work in that temperature. Specific pH value. But these polymers, because they are kind of designed in a different way, they are very, very good at also working under what we call extreme environments. So high temperature, low pH, etc. So I just seem like, I think there's like a little question here on, like, if you've got two molecules that are very similar, so glucose and galactose, if you can discriminate between them, and the answer is yes. Because I mainly focused on detection where we look at size and shape, but that's not the only interaction. If there's something in the chemistry that's different, and I don't know that on the top of my head from glucose and galactose, then we can modify our mixture, so our kind of recipe materials, fixates kind of around that. So you are able to look at molecules which are exactly the same in size, but by just adapting it by changing the chemistry. So hopefully that is a bit clear. For people who know more about the science, there's a lot you can kind of read about that. Actually, for bacteria, this is much more complicated. But bacteria also have other groups on like the outside of the surface of the membrane. So you can look at different groups that we've got there. So to recap, we have like a type of like a thermometer. It's the same as a normal thermometer. And then we've got this smart polymer plastic material, which you then can very well recognize specific things. And if you wanted to do that like in a really simple way, chemical engineer, not necessarily chemist, you can just, let's say, take a little thermometer and you can assemble some of the particles around it. So imagine that you would have like a thermometer which measures your temperature, and then we just modify this with the polymer material, which you can do in different ways. If you do it in a very, very simple way, I could just say, because this is like, these particles are so small that you can't see them by the eye, but they dissolve in water. So you would essentially have like a solution with water in which you've got the polymer material. And then you just put a drop of water on the surface and you let it dry. And then slowly you would form like a polymer kind of layer on top of it. So to explain what happens in these polymers, I'll just have to show you the surface. So imagine I said that I've got like these big cavities. So imagine that we've got something which has these binding sites here. Okay, and now imagine we apply temperature or heat fluid. You would see that it can just freely pass through here. Okay? So I used to tell my students, it's like heat and electricity, they always find the path of the least resistance. So it will freely flow through. Now imagine now we have the same surface. But then we have something which is bound to it. So I'm just exaggerating this a little bit because it's easier. So hopefully you can see this. So imagine we have our bacteria or a virus binding to it. And then all of a sudden the heat that would normally go through, or the electricity, it's kind of being blocked. Whereas if you have like an empty site, you can see it can still freely go through. Is that clear so far?
Yeah.
Good. Okay. Now, what we do is we measure the temperature at 2 different places. And this is where the thermometer comes in. We have a temperature which you measure, or a temperature we apply, which is here at the polymer material. So let's say normally we use 37 degrees because that's the normal temperature our body works in. Now we also measure in the liquid. So if we have, like, imagine you have a liquid here. Oop. There we go. We also measure, like, you see some binding here, just above this, just above the polymer surface, we also measure in the liquid. Okay? Now, what hopefully we should see, we have like one temperature, which is a control temperature. So let's say that's the temperature that we adapt. So that's normally 37 degrees. It can be a different temperature, but because we work with these elements, we assume let's use the same as what you would have in your antibodies. Now, if you get binding, this temperature just above the liquids, it should go down. And the way you should see this, if we've got these holes, and we normally have free heat that can kind of go through the holes, but then all of a sudden you've got something in there which isn't quite as conductive. So think of like a big bacteria or something else. So because you add something to the surface, which is like an extra layer of kind of resistance, the temperature just above it, so this temperature is not changed because remember this is the temperature that we put it at. This temperature is normally a little bit lower than the temperature, because this is the temperature in the liquid, than the temperature we put it at, because you always lose a little bit of heat. But this one should go down. So in essence, what you will see, you have these blocking of these polymer cavities. And because you do that, slowly you start affecting the temperature. And the more binding you get, the lower that kind of temperature is going to be, because the more you start blocking the material with something else. Is that how is that working?
Yeah.
Well, if there's any questions in between, just let me know. So in essence, to kind of tell you that we've got something that measures the temperature, which hopefully you can imagine that something that measures the temperature is very cheap, because we all have thermometers in our home, okay? So nothing really complicated. And then we combine that with something that is very kind of specific. So these are these polymers, and make it very selective, that we only see these changes in temperature when we want to detect binds. So we've got something all of a sudden which is very selective only towards, for instance, and I think I mentioned in the talk, we looked at heart attack. So we looked at cardiac biomarkers, and in that case you can measure something which is what we call troponin, because troponin is basically a protein which is released when you get damage to your heart muscle. So the more you can kind of release it, you will see that the higher the level of that is, that's an indication there's more damage to your heart. So it indicates that there's a heart attack. And quite recently, we use this to apply this also for detection of bacteria and viruses. So we've looked at, for instance, as many people have done, looking at COVID-19 with the idea that the lateral flow tests that we've got at the moment, they're not very sensitive. So they're very good at, you know, when you get the result, it might miss some of the earlier detection. So if you've got a relatively low viral load, and also because you have to put this in your nose, and everyone obviously does that in a slightly different way, there's a lot of variation in the results that you get. So the test that we hope tends to be like a lot more, what we say, like objective, in the sense that you get more results. It's just as fast, so it takes us still about, measurement usually takes about 15 minutes. But it's something that should hopefully be a lot more low cost, and it can also work under different circumstances. And the key thing that might be of interest here is that, imagine now we have these throat and nose samples, which is not very pleasant for a lot of people, especially if you think about kids. You know, no one is really happy putting a stick up their nose. So we potentially think that we can use something like that to measure something which is a little bit more challenging, such as, for instance, saliva, which is really very difficult to do when you work with these traditional lateral flow tests. I've seen there was a kind of a question before that, but I didn't quite fully get to read it. I just saw it.
Yeah, it says, yeah, I'm gonna read it for you. It says, other methods for measuring such as QZM is
Yes.
accurate like temperature.
Yes. Okay, so if there are other methods, yeah, of course. So the polymers that we work with, the binding that you get in the polymers, you can measure in many different ways. You could, for instance, use something, imagine, I think most people know like a glucose test is probably the, well, if you've seen the lateral flow test, you've got color changes. If you've got something like people with diabetes, they want to test their glucose level, and then you look at an electrochemical signal. I think the method that's mentioned here is, I'm not sure many people will know it, so I'll just try and briefly kind of explain how it works. It's a quartz crystal microbalance, a QCM. And what it does, it's very sensitive to changes in weight. So essentially, like we used to do this test where we would also take like one of these Sharpies and then we put like a little dot on there. So essentially, you know, this isn't very much, no, it's a tiny, tiny amount. But that's essentially something that can very sensitively detect small changes in weight. So like a little, you know, I put something here, for instance, just put it on my electrodes, and that would be enough to detect a change in something. So the same applies to you know, these type of polymers. If we would have like some binding in there, and then we have changes in the weight, a quartz crystal microbalance, so you can hear the word balance, like scales, it will be able to detect changes. But it's not, you can get like other type of devices. It's not something which is quite as cheap yet as the thermometers that we work with. Not often quite as portable. I know there are devices that are a little bit smaller. What we're really keen to have is like something that everyone can use. So like a device that you would be able to give to anyone in your home, or for instance, anyone in the hospital, that they can operate and they can very easily see what's happening. And that's obviously why color changes in these lateral flow tests are ideal, because everyone will understand there's a change in color, this is what it means. And with the QCM, the interpretation is slightly more difficult because you have to do a little bit more modeling. So yes, it does work. And I present this here because my work is mainly focused on this type of thermal detection, because that's, I think that's ideal, because it's only a thermometer, it's really cheap and easy to do. But there's many other different ways of doing it. And one of the other questions that I've seen, like, ideally, I think like, let's say we've got like our smartwatches now as well, no? So there are many different ways for people to look at, or for instance, in your sweats, you can monitor things. The problem with a lot of the tests that you have, if you measure glucose for people with diabetes, is that you still need to do a finger test. And if you do that once, that's okay. And you might not think it's too bad if you do it once every day, but you can imagine, especially the older you get and the more you need to use of it, it is unpleasant, because it's still like, you know, you're still damaging your fingers. So it's just an unpleasant, inconvenient thing to do. So ideally, it's the same as when you use, like, for instance, you sample from your nose and your throat, no one likes doing it. So there's definitely like a demand for a lot of tests to use something, for instance, what we call non-invasive. So that can be, for instance, if you measure things in sweat, or it can be something like, for instance, your watch, where you can very quickly get a signal and you wouldn't need to take like a blood measurement. So what the question was here is if we can look at interstitial fluids, and I have to kind of explain, I think, what that is. So within your top layer of your skin, just below the top layer of your skin, you have something which is called interstitial fluids. So it's before you get to the blood. So it's a very thin layer under your skin. And nowadays there are different ways of how you can actually access that fluid without damaging the skin. So people might know this, for people with diabetes, you've got like a certain type of patches. Like for instance, Abbott has made like a patch. And the advantage when you're not continuously using blood or damaging your skin is that you can continuously monitor things for a longer time. And people can do that in that case of glucose for up to 1 or 2 weeks. So which is helpful because, you know, glucose levels change quite fast. And you could imagine that if you look at, for instance, processes such as like when you want to monitor a heart attack, you don't want to constantly draw blood from patients. But if you use something like this interstitial fluids, or if you would, for instance, use sweat, then you can, over like a very long period, kind of collect the data, and it might give like a warning sign to like a doctor or someone else. So the way you would do it, I don't think you would necessarily, so these are polymers, so they're still foreign kind of objects. And anything which we know that is foreign that goes in the body, you need to make sure that our body doesn't reject it. So what people tend to do, I don't really know of examples of these polymers that have been implanted in the body. People have been doing tests with animals to show, in principle, the material that we use is very similar to biological material. So you would think, you would hope that it's kind of tolerated by our body. But the thing is, what you can do is if you would have like a device which would take something non-invasively, so as I said, for instance, sweat, or like the comment that was made on this interstitial fluids, where you take something without you actually feeling it, someone spraying through your skin, then that might be very interesting to look at things. And we are kind of considering these options for the project, where we look at, for instance, cardiac biomarkers, because it's not so interesting to know in real time what's happening, for instance, when you've got like a bacteria or a virus. But it would be really interesting to look at things that, for instance, the function of kidneys of people, if they are at higher risk of getting a heart attack, then that might be like a trigger to say that something is wrong. And you would hope that this is convenient for people, so they wouldn't necessarily have to worry about, you know, as I said, constantly doing these blood tests. And ideally, a lot of these things have come up because since the pandemic, it is harder to go to your GP all the time, or to go to the doctor, or to go to the hospital. So there's definitely like a lot of people wanting to have something which is essentially like a smartwatch, but then kind of telling them what's happening in their body. And we are particularly interested to use these polymers for it because, as I said, they are cheaper. And ideally, you could have like a selection of polymers. So you could use a selection of different markers and monitor all of that at the same time. Does that answer the question somewhat? I know it's a very...
Okay. Before asking our questions, there is another question that says, can we apply MIP in ISF under skin?
Yeah, no, I think I just answered that question before.
Yes,
okay.
The interstitial fluid. It's a very scientific question, so hopefully I try to explain it in such a way that people kind of understand how it works. And I do think when it comes to sensors in general, there is, at least here, there's a real drive to go away from blood measurements. And the way I try to pitch the type of sensors that I worked with before is like, if some people might have seen, like in Star Trek, you had when you went to the doctor and you had this kind of scan where they were just kind of scanning people and you could directly see what's happening. And ideally, you want something quite as futuristic as that, where there's no need for lots of complicated blood tests. You would have something where you can directly, without having inconvenience for the patients, to kind of monitor what's going on. So that's ideally what we kind of like to do. So thanks for that question. And I think it's very challenging from a technical perspective, okay? Because you can imagine that it's still like the skin you have to go through. But that's definitely something that we're very, very interested in. So a very interesting question.
Yeah, that's a very interesting question. So you were talking about also the biological compatibility of these polymers, right? Mm-hmm. So I guess you're working on this. So have you already had experiments or like any experience with this already, like with these polymers in the human body?
I think the closest we've come to that is because, and usually at the university, we kind of work at the level where we do research But we work a lot with companies. So we work with a couple of companies that are very interested in that. What we have done, for instance, in the work of the COVID-19, we looked at patient samples. So we looked at, for instance, 10 samples of patients with the Delta variant, and then we compare it to what's already out there. So we look, and in our case, we compare it to PCR tests. So because we always need to check if our technology is working. So we've done that. And for the cardiac biomarkers, where we looked at when people can, are at risk of a heart attack, we look at blood samples, because that's the kind of common standard. You would normally take blood samples every specific times, and normally you would see something where you see this kind of gradually going up, which is an indication that people have a heart attack. So again, there we looked at, and this is still very much work in progress, because as a scientist, it's very difficult to get approval to measure patient samples. So it's very complicated to do all of that, where we kind of there looked at blood samples. And that's, I think, the closest that we normally get to working with patients. But there's one specific example, but that's with my PhD supervisor in Belgium, where we're actually going to work with patients. And in this case, we're not going to look at blood or for instance, other samples that come from outside the body. He has developed a type of catheter. So catheters are used to check whether you have problems in your bowels. And he has developed a new design where we can coat our polymer particles onto this type of catheter. And this catheter has to go, so you have to imagine, it goes for your nose, has to go all the way through your stomach, and then it has to go inside your bowels in order to measure. So your stomach is extremely acidic. So anything you can imagine that you want to measure usually gets absolutely destroyed in there. But he's made a very clever design where we have something which is around the catheter, so it's kind of protecting the polymers. And then only when it gets in the right position, so this is where you can measure what's happening. So that's something that's going to be tested in patients. And that's the work in Belgium that people actually have approval for now. And that will be very exciting. And I very much look forward to see those results.
That's pretty interesting. And also, like, what components makes these polymers to be not that hard or bad for our bodies? Because you talk about like tests in animals, right? Like experiments in animals already. So like, how is it different? And what kind of animals have been already used for this?
I haven't looked at animals myself. Okay, I know there are certain tests. Normally you would start with small animals, so you would look at, for instance, rats or mice. And what you would normally look for is that when you administer, like what people have done is, if you have bee venom, which is not, it's very inconvenient for us, but you can imagine this is very dangerous to small animals, because they don't weigh so much. So if they get the same amount of venom as we would get, their bodies really struggle to cope with that. So what people have done is they can, because I said these are soluble in water, so you can inject, in principle, these particles, and then you want to look what happens in your body when you get it. So in the worst case, this would go in fatty tissue, because that would mean it doesn't leave your body. It kind of goes to places where you don't want it to be. What normally in our body actually takes care of cleanup of things, that's our liver. So what they would actually see is when they included these polymer materials, so they injected it, and they could trace this with something fluorescent. So they added something to the polymer so they could do some imaging, so they could see where it was in the body. In that case, they saw it went to the liver, where it was broken down and metabolized. So this is how people have been checking to show what we call, which is biocompatible. But normally, before you go to animal tests, because you want to use as few animals as possible, you would check this, what we call with cell lines. So these are kind of artificial systems that maybe come from humans or from animals, but you don't have to use the animal itself. So you use that first, and then you would mix in those cells with your polymers, and you would want to check whether the cells are still growing. And if they wouldn't, then that's an indication that it's bad. and that it has an impact on us. So first you would normally do these experiments before you go to animals.
That's pretty interesting because you know, people who are not that into science, we tend to think like all experiments, like they go first of all through animals and then they test this kind of way. So that's pretty interesting to know.
Okay, I quickly need to find, because my battery apparently is running low. So I'll just, while you're talking to me, I'm trying to find the best place where I can plug in my phone. But that should be okay.
It's okay.
Good. Have you got any other questions that I can help with?
Well, first I would like to thank you for this wonderful speech, and it's very interesting and very important and very relevant because Marloes?
There we go. Yes, sorry.
Well, I work with cardiologists, and I've been told that as high as 30% of people that have heart attacks have normal ECG at the beginning. So they go to the hospital, the emergency rooms, and the first thing they do is an ECG, and 30% of them are normal, but yet they have a heart attack. So if there are symptoms, they will go and check some proteins, some biomarkers, and this takes maybe 1 hour or even a little bit more. Yeah, to have the results, and in this 1 or 2 hours, we don't know if there is a heart attack or not. And even these biomarkers, some of them, they give only high levels after 12 hours.
Yes, that's true. Yeah.
That the heart attack started. So when the obstruction of the artery happened. So this the biomarker that you are using is troponin, yes? Is it when the heart attack starts, how long does it take to this biomarker start to grow up in the level?
No, you're absolutely right. From what I know working with cardiologists that we know is they say not everyone has these typical symptoms of a heart attack. And they say particularly in women, they don't have this, people usually think of acute chest pain. And that's clearly, for a lot of women, that's absolutely not the case. So the typical symptoms that we think of a heart attack are not always there. So that's important to recognize. There's always a little bit of delay in seeing things. So what I've been told, and as I said, I'm not a doctor, I'm an engineer, but they said there's normally what they call like a golden hour. And in that hour, there's supposed to be symptoms that are reversible. So the sooner you find it, and especially for when you have a heart attack, it's important to find it as soon as possible, because then you can still treat it very well. And the longer you wait, as you know, the more difficult it becomes. And the biomarker troponin is the standard one. This is what people kind of tend to use all the time. But there's still a little bit of delay in that. So the key thing that you would want to use with the polymers that we have is to use a kind of almost like a cocktail of different markers, because some you have quite early onset. The good thing about troponin is that it's very specific to the heart, because there are a lot of other markers that are general for inflammation. And you would kind of together also. So ideally you'd want to check for like a combination of different ones. But yes, they do kind of acknowledge it's very important because especially now a lot of people think like, well, I didn't really have a lot of pain, or I didn't have so much symptoms. So having something like that would give like a kind of like an early trigger that something is actually wrong, and the sooner you would get this, the better you should be able to treat people.
Yes, the problem is to discard the people with heart attack because the ECG was normal and some tests gave normal.
Yes.
And well, then it's very dangerous, of course.
Yeah. There's that. There's also a lot of people who are like, I had this before. I had a colleague who had like a really bad muscle pain. which is exactly the same as having chest pain. So there's also a lot of people that actually don't have a heart attack, but they have really serious symptoms. So it's also a good way to quickly screen if people actually have a heart attack, and if they don't, you can send them home earlier, which is much better, for instance, in hospitals, because they're already, I'm sure the emergency rooms are already very crowded. So you want to make sure that you target absolutely the right people, and that people, you can also reassure them maybe earlier if something is not wrong. Because often these people will need to be admitted and they need to stay overnight in the hospital, which really is, puts a lot of strain on the hospital and the people working there.
Yes. Rebecca, do we have more questions, or would you like to ask anything else?
Well, I was taking some notes, and then I have something here. Yeah, I have something here like this system, can it recognize any bacteria?
The polymers, if they can recognize bacteria. Yes.
Yeah, any bacteria.
Well, any, yeah. So I think bacteria are quite challenging because they are quite, for instance, if you have a bacteria that's a normal one and a resistant one, they're not so, the genetic sequences is different, but on the outside they look relatively similar. So with bacteria, you can definitely recognize them, and there's people working on it, but it's very difficult to discriminate between different bacteria because the changes between them can be so small, and the polymers do need to work with something which is different on the outside. So something on the surface needs to be different. So I would want to say that I think the technology is much better established for instance, very small molecules like pharmaceuticals, and also with viruses, we very well know kind of what's different on the surface. And with bacteria, it's a bit more challenging. But there are people, for instance, who looked at detecting cancer cells, and cancer cells tend to have a lot more sugar on the outside, and using that to discriminate between healthy cells and cells that have cancer.
Okay.
Any other question, Rebecca?
Well, the last note that I have in here is something about the quartz crystal microbalance. So, this system works with this, and how, like in a simple way, how can we transmit or try to say this to people that are not really quite, they don't really have a quite big knowledge about science, this quartz crystal microbalance?
Yeah, so I think, you know, I work with temperature sensors, but I think the easiest thing where you can make a small device, which is really portable and handheld, is obviously still something which is similar to the sensor that you've got for detection of glucose in the case of diabetes. So something electrochemical, you can make it very, very small. So you can make it handheld, and you know, it's kind of like roughly this size, isn't it? So I think that's probably when it comes to being able to do a test in your home. And I recognize the technology that I work with. It's not commercialized, so you can't just buy like a device from the shelves and say like, I've got this at home. So I think the electrochemical detection is probably the most promising route for doing this at home. And that's kind of what we're doing at the same time, is that we make our polymer particles, and then we add in something which also has, it has some electrical behavior. So it will change when you get binding to the polymer as well. But that's a bit more challenging, because we need to make sure that whatever we put in the material still make sure that what we want to detect can still bind to there. So I think that's probably the future will be in that type of sensors that have like a similar makeup to either like a lateral flow test where you've got an optical signal, or something where you can, in the case of a glucose sensor, you don't even see the electrochemical detection, but you just see a number that comes up, you know. So they use there the current to link this to a specific concentration.
Perfect. So do you think that this system is going to be out soon?
My system. No.
Yeah.
So the polymers I work with, there are some commercial examples, but they are not available for sensors. So they are there, for instance, you can buy from Sigma Aldrich, which if you are a chemist, you know it's a very common website from which you can buy chemicals. So in that case, you can get these polymers which can be used to purify and to mixtures. So people have made these polymers for the cleanup of, for instance, water samples, where you can get rid of certain hormones and certain pesticides. So in terms of using it for purification or those kind of things, there are already examples out there which you can find. When it comes to sensors, this is quite tricky. Okay, you can have a look at one of the companies that I work with. Is called MIP Diagnostics, and I think the name already says it. Diagnostics is sensors. So from them you can buy, for instance, these particles that are very selective for certain things. But there's no such kind of sensor system out there yet. You buy it as a sensor. You don't buy it as the polymer material. But I do think that this will come out in the next couple of years. But it won't come via the university. It will always come via working with these companies.
Okay. Yeah. It's really futuristic and it's really interesting all. And as Jonas says, it was a wonderful speech. So we really appreciate all of this. Thank you very much. And Jonas, do you have any questions?
No, I don't have any questions, and I just want to thank Marloes for participating from this project with such a nice talk. And thank you very much.
No, you're welcome.
Okay.
Hopefully we will get to see more Brazilian students soon enough.
Oh, yes. I have just selected two. You will get the email today.
Perfect.
With their names and everything, yes. And thank you for accepting our students for these internships. This is very important for them. They come back very happy and say that they learned a lot, and it's wonderful. Thank you very much for this.
Yes, and thanks for both of you for the invitation.
Okay, so can we close now, Rebecca?
Yes. So thank you everyone that saw this and asked questions. We really appreciate this. So see you in the next live. Bye-bye, everyone.
Bye-bye.